Good morning, everyone. I'm Yufei from Harbin Institute of Technology. I'm delighted to present my work here at IEEE Sensors 2025 in Vancouver. Today's topic is an optimized sparse calibration algorithm for magnetic sensor arrays, a solution designed to address efficiency constraints in calibrating magnetic sensor arrays. Let's dive into the details. Capsule robots are an emerging tool for gastrointestinal cancer screening and treatment. Compared with traditional endoscopy, they are painless, non-invasive, free from cross-infection, and unaffected by patient movement. Of different localization techniques, magnetic field-based ones stand out for their reliability and commercial potential. For reliable field modeling and precise localization, accurate sensor array calibration is key. Conventional calibration places a magnet at no position near the array, then estimates sensitivity via least squared. This needs precise positioning and often external equipment like optical tracking system, making it complex and slow. To simplify, Wu et al. Proposed a rotational method that avoids known position, using PSO agriculture for poles and the LM algorithm for sensitivity updates. Also, this removes tracking system. It requires optimizing 6 degrees of freedom, causing slow convergence and long calibration times, often over 15 minutes. Then et al. Improves speed using a direct solution with big angle constraints, but needed a more complex tool. This paper proposes a fast calibration method based on a novel universal joint-based calibration tool. By reducing the number of optimization parameters from 6 to 2, the method enables rapid calibration of magnetic sensor arrays. As shown in picture 2, the calibration tool is a rigid structure connected to a base via a universal joint. This allows the magnet to rotate along the surface of sphere center at the joint with radius L. All our sampling points sit on a sphere, right? So for the magnet at the I sampling point, we don't need to use a bunch of parameters. We just use two angles, alpha I and beta I, to describe where it is, which way it's facing. Let me break those angles down. Alpha I is the project angle. Basically, if you project the magnet direction onto the xy plane, this angle tells you how it lines up with the x-axis. And beta I is the elevation angle. That's how high the magnet is tilted up from the xy plane. Now, these two angles are linked to the 6-dimensional coordinates we usually use. The specific relationship is shown in this picture. Now, let's walk through how we actually do the calibration. First off, before we even start the main calibration, we need to do a few pre-steps. The first one is getting the sensor array ready and notice down the ambient magnetic field value. Think of this as checking the background noise of the magnetic field around us so we can account for it later. Then we set up the calibration tools and record the coordinate of the pivot point. After that, we put the magnet in, spin around a bit, and collect magnetic field reading at different points. So we are gathering all the real data we need to calibrate. Once we have that data, we move into the co-calibration process, which follows the flow chart you see here. First, we take those magnetic field reading. B, we just collected from each sensor at every sampling point. Those are our main inputs. Then we start by giving an initial value to K. That's the sensitivity we are trying to find for each sensor. Since that's key to accurate calibration, next we clean up the data. For each sampling point measure V, we subject the ambient geometric field we noted earlier, the background noise. So we are only looking at the magnetic field from the magnet itself, not the surrounding environment. After cleaning the data, we check if the arrow is good enough. If not, we keep refining things. First, we update the angles alpha and beta. We talked about earlier, using the LM algorithm to find the best possible alpha and beta to minimize the error between our model and the actual magnetic field from the magnet. Once we have those updated angles, we then use this square to update the sensitivity K, making it more accurate. Then we look back to check the error again with this new K and new angles. We keep doing this back and forth, updating angles, updating K, checking error, until the error is small enough. So by the end, we have all the value we need to make sure the sensor array working accurately for localizing the capsule robot later on. To test if our proposed calibration algorithm works, we build a magnetic sensor array and a calibration tool. You can see them in picture. First, let's talk about the magnet. We use a cylindrical permanent magnet that magnetizes along its axis. The sensor array has 16 triaxial magnetometer. The model is LIS3MBL. Each of these sensors can measure magnetic field from 0 to 12 volts, and they can take 20 readings per second. We arrange the sensors in a square grid with 4 centimeters between each sensor. Altogether, the array covers an area of 12 by 12 centimeters. And to get the data and process it, we connected all the sensors to a computer using a USB cable. Super straightforward to set up. During the experiment, we rotated the calibration tool by hand and collected several groups of samples. For each group, we recorded around 115 sets of magnetic field data, and that took about 7.5 seconds total. Then for each sample group, we ran the LM algorithm through 30 rounds of iteration. On average, each round took 13.98 seconds. Looking at this picture, it shows how sensitivity coefficient K changes as the iteration go on. And here's a key point. K basically stops changing. We call that converging after about the 10th iteration. So we don't even need to do all 30 iterations to get a stable K value. It settles down pretty quickly. After calibration, we test the accuracy of our LM-based magnetic localization algorithm by sampling at preset fixed position. We already knew the real location and orientation of these positions, so we could compare them to what the algorithm estimated. To measure accuracy, we define two types of arrows, P arrows for position and O arrows for orientation. We use two 6 three vectors here, one for the actual position and orientation, and one for the estimated one. The actual vector is A, B, C, and N, P. A, B, C are the real position coordinates, and M and P are the real orientation values. The estimated vector has the same form, but with little heads on top of each letter. Those letters with heads stand for the algorithm's estimate position coordinates and orientation values. P arrow is the 3D straight line distance between the actual and estimated position. It's calculated as the square root of A minus the estimate A squared plus B minus the estimate B squared plus C minus the estimate C squared. O arrow is the angle between the actual and estimate orientation vectors. Is calculated as the absolute value of r cosine of n times the estimate n plus n times the estimate n plus p times the estimate p divided by the square root of n squared plus n squared plus p squared multiplied by the square root of the estimate n squared plus estimate n squared plus estimate p squared. Our figures show the arrow distribution and the key numbers tell the story. The average P arrow is 1.96 millimeters, and the average O arrow is 2.79 degrees. These small values prove our algorithm works well. To wrap up our magnetic sensor array calibration work, our main goal was to make rotational calibration more efficient, so we proposed a new optimization algorithm. What makes it stand out? First, it kept the number of optimization parameters. Crucially, it still keeps traditional method key age. No need for detailed magnetic source info. That's a big plus, as it avoids the hassle of remeasuring or knowing every source detail. In performance, we've shortened calibration time to around 30 seconds, a significant improvement over longer processes. Also, the method is simple. It only needs 2 DOS spherical rotation, no complex mechanical setup or actual step. We pair it with a portable calibration tool, so it works in many scenarios, not just basic labs. All in all, this new approach is both efficient and practical. It meets the need for faster calibration while staying simple and adaptable. Valuable for real-world use of magnetic sensor array. Thank you for your attention.